Music and mathematics. Music theory analyzes the pitch, timing, and structure of music. It uses mathematics to study elements of music such as tempo, chord progression, form, and meter. The attempt to structure and communicate new ways of composing and hearing music has led to musical applications of set theory, abstract algebra, and number theory. While music theory has no axiomatic foundation in modern mathematics, the basis of musical sound can be described mathematically using acoustics and exhibits a remarkable array of number properties. History. Though ancient Chinese, Indians, Egyptians, and Mesopotamians are known to have studied the mathematical principles of sound, the Pythagoreans, in particular Philolaus, and Archytas of ancient Greece were the first researchers known to have investigated the expression of musical scales in terms of numerical ratios, particularly the ratios of small integers. Their central doctrine was that all nature consists of harmony arising out of numbers. From the time of Plato, harmony was considered a fundamental branch of physics, now known as musical acoustics. Early Indian and Chinese theorists show similar approaches. All sought to show that the mathematical laws of harmonics and rhythms were fundamental not only to our understanding of the world, but to human well-being. Confucius, like Pythagoras, regarded the small numbers 1234 as the source of all perfection. Time, rhythm, and meter, meter, and meter, and meter, and meter, meter. Without the boundaries of rhythmic structure, a fundamental equal and regular arrangement of pulse repetition, accent, phrase, and duration music would not be possible. Modern musical use of terms like meter and measure also reflects the historical importance of music, along with astronomy in the development of counting, arithmetic, and the exact measurement of time and periodicity that is fundamental to physics. The elements of musical form often build strict proportions or hypermetric structures, powers of the numbers 2 and 3. Musical form. Musical form is the plan by which a short piece of music is extended. The term plan is also used in architecture, to which musical form is often compared. Like the architect, the composer must take into account the function for which the work is intended and the means available, practicing economy and making use of repetition and order. The common types of form known as binary and ternary twofold and threefold once again demonstrate the importance of small integral values to the intelligibility and appeal of music. Frequency and harmony. A musical scale is a discrete set of pitches used in making or describing music. The most important scale in the Western tradition is the diatonic scale, but many others have been used and proposed in various historical eras and parts of the world. Each pitch corresponds to a particular frequency, expressed in Hertz Hc, sometimes referred to as cycles per second cps. PS, 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 PS. Yes. S. A scale has an interval of repetition, normally the octave. The octave of any pitch refers to a frequency exactly twice that of the given pitch. Succeeding superoctaves are pitches found at frequencies 4, 8, 16 times, and so on of the fundamental frequency. Pitches at frequencies of half, a quarter, an eighth, and so on of the fundamental are called suboctaves. There is no case in musical harmony where, if a given pitch be considered accordant, that its octaves are considered otherwise. Therefore, any note and its octaves will generally be found similarly named in musical systems, e.g., all will be called do or sa, as the case may be. When expressed as a frequency bandwidth, an octave atwo A3 spans from 110 Hz to 220 Hz span equals 110 Hz. The next octave will span from 220 Hz to 440 Hz span equals 220 Hz. The third octave spans from 440 Hz to 880 Hz span equals 440 Hz, and so on. Each successive octave spans twice the frequency range of the previous octave. Because we are often interested in the relations or ratios between the pitches known as intervals. Rather, for interval size comparison, cents are often used. Tuning systems. There are two main families of tuning systems: equal temperament and just tuning. Equal temperament scales are built by dividing an octave into intervals which are equal on a logarithmic scale, which results in perfectly evenly divided scales, but with ratios of frequencies which are irrational numbers. Just scales are built by multiplying frequencies by rational numbers, which results in simple ratios between frequencies, but with scale divisions that are uneven. One major difference between equal temperament tunings and just tunings is differences in acoustical beat when two notes are sounded together, which affects the subjective experience of consonance and dissonance. Both of these systems, and the vast majority of music in general, have scales that repeat on the interval of every octave, which is defined as frequency ratio of 2:1. In other words, every time the frequency is doubled, the given scale repeats. Below are Ogg Vorbis files demonstrating the difference between just intonation and equal temperament. You might need to play the samples several times before you can detect the difference. Two sine waves played consecutively. This sample has half step at 550 HCC# in the just intonation scale, followed by a half step at 554.37 HCC# in the equal temperament scale. Same two notes set against in a 440 pedal. This sample consists of a dyad. The lower note is a constant of 448 C in either scale. The upper note is a C# in the equal tempered scale for the first one, and a C# in the just intonation scale for the last one. Phase differences make it easier to detect the transition than in the previous sample. Just tunings. 5-limit tuning, the most common form of just intonation, is a system of tuning using tones that are regular number harmonics of a single fundamental frequency. This was one of the scales Johannes Kepler presented in his Harmonices Mundi 1619 in connection with planetary motion. The same scale was given in transposed form by Scottish mathematician and musical theorist Alexander Malcolm in 1721 in his Treatise of Music, Speculative, Practical and Historical, and by theorist José Wiewerschmidt in the 20th century. A form of it is used in the music of northern India. American composer Terry Riley also made use of the inverted form of it in his Harp of New Albion. Just intonation gives superior results when there is little or no chord progression. Voices and other instruments gravitate to just intonation whenever possible. However, it gives two different whole tone intervals 9, 8, and 10. 9 because a fixed-tuned instrument, such as a piano, cannot change key. To calculate the frequency of a note in a scale given in terms of ratios, the frequency ratio is multiplied by the tonic frequency. For instance, with a tonic of A for a natural above middle C, the frequency is 448 C, and a justly tuned fifth above it F is simply 443, 2 equals 668 C. Pythagorean tuning is tuning based only on the perfect consonances, the perfect octave, perfect fifth. Thus the major third is considered not a third but a ditone, literally two tones, and is 9, 8 equals 81, 64, rather than the independent and harmonic just 5, 4 equals 80, 64 directly below. A whole tone is a secondary interval being derived from two perfect fifths minus an octave, 3, 2/2 equals 9, 8. The just major third, 5, 4, and minor third, 6, 5, are a syntonic comma, 81, 80, apart from their Pythagorean equivalents 81, 64, and 32, 27 respectively. According to Carl Dahlhaus 1990, p. 187, the dependent third conforms to the Pythagorean, the independent third to the harmonic tuning of intervals. Western common practice music usually cannot be played in just intonation, but requires a systematically tempered scale. The tempering can involve either the irregularities of well temperament or be constructed as a regular temperament, either some form of equal temperament or some other regular mean tone, but in all cases will involve the fundamental features of mean-tone temperament. For example, the root of chord Roman 2, if tuned to a fifth above the dominant, would be a major whole tone 9, 8 above the tonic. If tuned a just minor third 6, 5 below a just subdominant degree of 4, 3, however, the interval from the tonic would equal a minor whole tone 10, 9. Mean tone temperament reduces the difference between 9, 8 and 10, 9. Their ratio 9, 8/10, 9 equals 81. 80 is treated as a unison. The interval 81, 80, called the syntonic comma or comma didymis, is the key comma of mean tone temperament. Equal temperament tunings. In equal temperament, the octave is divided into equal parts on the logarithmic scale. While it is possible to construct equal temperament scale with any number of notes, for example, the 24-tone Arab tone system, the most common number is 12, which makes up the equal temperament chromatic scale. In Western music, a division into 12 intervals is commonly assumed unless it is specified otherwise. For the chromatic scale, the octave is divided into 12 equal parts. Each semitone half step is an interval of the 12th root of 2 so that 12 of these equal half steps add up to exactly an octave. With fretted instruments it is very useful to use equal temperament so that the frets align evenly across the strings. In the European music tradition, equal temperament was used for lute and guitar music far earlier than for other instruments, such as musical keyboards. Because of this historical force, 12-tone equal temperament is now the dominant intonation system in the Western and much of the non-Western world. Equally tempered scales have been used and instruments built using various other numbers of equal intervals. The 19 equal temperament, first proposed and used by Guillaume Costelli in the 16th century, uses 19 equally spaced tones, offering better major thirds and far better minor thirds than normal 12 semitone equal temperament at the cost of a flatter fifth. The overall effect is one of greater consonance. 24 equal temperament, with 24 equally spaced tones, is widespread in the pedagogy and notation of Arabic music. However, in theory and practice, the intonation of Arabic music conforms to rational ratios, as opposed to the irrational ratios of equally tempered systems. While any analog to the equally tempered quarter tone is entirely absent from Arabic intonation systems, analogs to a three-quarter tone or neutral second frequently occur. These neutral seconds, however, vary slightly in their ratios dependent on makam as well as geography. Indeed, Arabic music historian Habib Hassan Tauma has written that the breadth of deviation of this musical step is a crucial ingredient in the peculiar flavor of Arabian music. To temper the scale by dividing the octave into 24 quarter tones of equal size would be to surrender one of the most characteristic elements of this musical culture. 50. Connections to mathematics. Set theory. Musical set theory uses the language of mathematical set theory in an elementary way to organize musical objects and describe their relationships. To analyze the structure of a piece of typically atonal music using musical set theory, one usually starts with a set of tones, which could form motives or chords. By applying simple operations, such as transposition and inversion, one can discover deep structures in the music. Operations such as transposition and inversion are called isometries because they preserve the intervals between tones in a set. Abstract algebra. Expanding on the methods of musical set theory, some theorists have used abstract algebra to analyze music. For example, the pitch classes in an equally tempered octave form an abelian group with 12 elements. It is possible to describe just intonation in terms of a free abelian group. Transformational theory is a branch of music theory developed by David Lewin. The theory allows for great generality because it emphasizes transformations between musical objects rather than the musical objects themselves. Theorists have also proposed musical applications of more sophisticated algebraic concepts. The theory of regular temperaments has been extensively developed with a wide range of sophisticated mathematics, for example by associating each regular temperament with a rational point on a grass menu. The chromatic scale has a free and transitive action of the cyclic group C, E, / 12, C, E, \maths, C/12 Z, math Z, math Z, if 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 Z, math Z, if Z, if Z, with the action being defined via transposition of notes. So the chromatic scale can be thought of as a torsor for the group. Numbers and series. Some composers have incorporated the golden ratio and Fibonacci numbers into their work. Category theory. The mathematician and musicologist Garino Mazzola has used category theory topos theory for a basis of music theory, which includes using topology as a basis for a theory of rhythm and motives, and differential geometry as a basis for a theory of musical phrasing, tempo, and intonation. Musicians who are also mathematicians. Albert Einstein, accomplished pianist and violinist. Art Garfunkel, Simon and Garfunkel Masters in Mathematics Education, Columbia University. Brian McQueen, BSc Hons in Mathematics and Physics, PhD in Astrophysics, both from Imperial College London. Dan Snaith, PhD Mathematics, Imperial College London. Delia Derbyshire, BA in Mathematics and Music from Cambridge. Johnny Buckland Coldplay studied astronomy and mathematics at University College London. Kit Armstrong, degree in music and MSc in mathematics. Manjul Bhargava plays the tabla, won the Fields Medal in 2014. Phil Alvin, the Blasters, Mathematics, University of California, Los Angeles. Philip Glass studied mathematics and philosophy at the University of Chicago. Tom Larrabier, mathematics from Harvard University. William Herschel, astronomer, and played the oboe, violin, harpsichord, and organ. He composed 24 symphonies and many concertos, as well as some church music. Jerome Hines, 5 articles published in Mathematics Magazine, 1951, Minus 6.